Hi guys, today we're going to be starting exam 3 and we're going to be talking about wet bulb temperature. So wet bulb temperature is when you wrap a wet cloth around a thermometer and you swing it around or move it so that air passes over. And now what this does, it returns the lowest temperature of the air due to evaporative cooling. So this has to do with humidity. Now, before we get into Lewis relation, I want to talk about and make the connection between heat flux and mass flux, which will be really important. So let's do that. So let's look at the heat flux equation. Now this is done in static conditions, which means it's not through convection, it's through conduction. So let's look at it. So here we have that heat flux, and then we have this thermal conductivity coefficient over this temperature gradient in relation to distance in the x direction. And then we have the mass flux with this diffusive coefficient. And this concentration gradient in relation to distance as well in the x direction. Now this is done by diffusion, and this one is done by conduction. So now let's look at equations for heat flux and mass flux, but now in a convective situation, so like that wet bulb condition. So we have the heat flux, and now that it's convective, we have that heat transfer coefficient, and then we have this temperature difference from the surface to some distance far away, so away from the surface. And now similarly, we have mass flux, for the mass coefficient and this concentration difference from the surface and then far away. Let's make this bigger. So now what we're looking at here, we can see that there are some parallels. So the structure of these equations are very similar. And so looking at the conductive and over here, we can see that we have this negative coefficient in front, and then we have, it's followed by a gradient. This one in relation to time, and this one in relation to concentration. But then looking over here at the convective, we can see that there's a coefficient in front again, and then followed by a difference. So in this case, temperature, and in this case, concentration. So now what so this is significant because it's easier to measure temperature for experiments in most situations, I would say, versus maybe in this case, if we want to find the mass transfer of water into air, you would have to measure how much is evaporated. That would be much more difficult than just taking a temperature. So by creating this analogy, it's ideal, and we'll talk about these parallels throughout the video. But what I want to talk about is the Nusselt number and the Sherwood number. So the heat transfer coefficient, and this is just some characteristic distance over that thermal conductivity. For the Sherwood number, we have that mass transfer coefficient, that characteristic distance, and that diffusive coefficient. So for exam 2, we talked about the Sherwood number, and in that case we had two unknowns. that mass transfer coefficient and that diffusive coefficient. So we had no idea what those were, and that's what we're trying to find. And so we did dimensional analysis, and through the Buckingham Pi method found three-dimensionless groups, and this was one of them. So if we did the same thing for that was for mass transfer, and we did the same thing for heat transfer, we would come up with this dimensionless group. And our unknowns are the heat transfer coefficient and that thermal conductivity. All right, so all I did was I got rid of those arrows, and now what I want to talk about is comparing these equations. And let's say we found data experimentally, and we created model fittings for both of those data. Those model fittings should be the same. So what we can do is show, let's say for example, I got 0.5 and then 0.26 times the Reynolds number to 0.3 to the Schmidt number to 0.41. Well, then we can say the same thing for those coefficients and exponents for the Nusselt number. So 0.5 plus 0.26 times the Reynolds to 0.3 power, and then instead of the Schmidt number, it will be the Prandtl number. So let's just look at those real quick. So the Prandtl number is just that viscosity over density times thermal diffusivity. And now for the Schmidt number, it's just that viscosity, density, and then that mass diffusivity. So really, just looking at these, the only difference is those diffusivities. And that's really significant. So the coefficients and exponents found experimentally, those are just made up numbers. And the important part is that under similar conditions, the heat transfer and mass transfer are comparable, and those coefficients and exponents will be the same for each other. So theoretically we could make predictions for mass transfer without having to perform any experiments. And that's significant because, like earlier I said, measuring temperature would be much easier than having to measure mass, maybe the mass of how much water evaporated. That's so much easier. So now further, what we can do is we can take that Nusselt number and divide it by the Sherwood number. And that would leave us with, let's make these generic equations. Prandtl. Oh, and what this just is that's just kinematic viscosity. You can simplify that. And then over Schmidt. And so looking at this, if we put these over one another, these will cancel. And that's also really significant because that means it doesn't matter what, sorry, let me backtrack for a second. Let me write out the Reynolds number and those variables in it. So that would be density, velocity, characteristic distance, and a viscosity. So that really means, like, it doesn't matter how fast you're moving it. It doesn't matter maybe how tight you put that cloth around, because that distance, it doesn't matter. That diameter, let's just say, doesn't matter. So that's also really significant for this comparison. And so now let's carry on. And so we see that it's just the Prandtl over the Schmidt number, which is also just this diffusivity coefficient over the thermal diffusivity if we look back and put those one another, those will cancel. And then that will give us 1 over the Lewis number. So if we just did the inverse and just did that alpha, that thermal diffusivity over the mass diffusivity, that would just give us the Lewis number. But it's also okay this way. So as a result, we would get the equation of density, that heat capacity, the mass diffusivity over thermal conductivity. So this is for looking at this, that Lewis relationship is really significant because for moist air we can estimate it to 1, and I will show you how to see that. So let's look at all the variables. So what I'm going to do here is I'm just going to say, so for air, the thermal conductivity is 0.03 watts per meters Kelvin. And then the density for air is 1.2 kilograms meters cubed. The heat capacity is 1,000. So remember, this is moist air. So this is that's the wet bulb condition. And this only really works for water and air, but that happens frequently. And then that mass diffusivity is that mass coefficient 3 times 10 to the -5th meters squared per second. So we can get it when we plug all these in to this equation, it will roughly come out to be 1. So for moist air, it's majority air. There's going to be some water in it, but it's majority air, and that's going to be significant. So it's that air and water out here, but at that surface, it's going to be just that water, and it's evaporating through the air into that air and water mixture.
All right, so lastly, I want to make a relationship between these variables we defined up here for the Nusselt and Sherwood number, and then the relationship of dividing those over here. So what I'm going to do first is I'm going to take these, and I'm going to divide them by one another, which is how they are. So just that Nusselt over the Sherwood number, and that will give us that H, characteristic distance, over that Kc, I believe. Oh, just K, that thermal diffusivity. All over the mass transfer coefficient, characteristic distance, over the diffusion coefficient. So you cancel those, and then you are left with H, diffusivity coefficient, C, so that mass transfer coefficient and the thermal conductivity. And then I also want to include what we have found from here. So since the Nusselt number and the Sherwood number we found equals 1 over that Lewis number, that means this expression must also equal that 1 over the Lewis number. And then we can also add this part here, where it's that density, heat capacity, diffusion over, the diffusion coefficient, all over that thermal conductivity. And we can see this relationship here, and we can cancel these out with one another. And then we're left with that heat transfer coefficient over that thermal conductive, that mass transfer coefficient is equal to that 1 over the Lewis number, which would just be rho Cp, that heat capacity, just gotten from here. So if we do the inverse, we could, if we do the inverse through Kc, for that H to equal Lewis number equal that 1 over rho Cp. And so that's just that 1 over the Lewis number is equal to that volumetric heat capacity. And we just draw that parallel from all the other variables we've worked through so far.